Hey there, my name is Justin Kidd. I'm a research scientist in Idaho Falls, Idaho. I work for JK Research, which is a partnership between myself and Abram and Ken Taylor. We have an office at Snake River Landing where we currently do magnetics research, looking into electromagnetic induction and permanent magnet arrays. I have something I wanted to take a video of just for documentation, show what it's doing, so that I have record of it, and also to share with some of my friends that think what I do is kind of crazy. So I would like to introduce to you the complex magnetic field array I call Boris. Boris is actually a compressed magnetic field where we have aligned the magnets, if you will, such that all of the north polarities exist on one plane, and the south polarities of the magnet of the south polar faces also align on a plane. So what does that look like? Well, I'll show you in just a second here. So that would be Boris. More specifically, this is a mechanism that I've developed to test a couple of theories that I have about the geometry of a magnetic field. Also to test my theory that the quantized electromagnetic field is basically like a power reservoir, that it is constantly being added to and taken from, and that when we put energy into it, it can store it for long periods of time, and that there is a vast reservoir of energy in hidden dimension within the magnetic field that we're familiar with, where we can go and mimic that geometry in a machine and be able to harness that power out of that hidden dimension, if you will. So as you can see here, we have Boris. You can see the top of Boris has all red markers, which indicates that each one of these is a north pole of a magnet. They are encased in PVC pipe, a kind of a clever mechanism to be able to add bolts to them to make them a modular system. And then I've used a piece of 3-inch diameter PVC pipe, drilled holes in it equidistant to be able to mount 10 of those magnet stacks here, as you can see, with each of the north poles aligned in one plane, and then on the bottom side, all of the south poles also aligned in the same plane. So you can see basically what has happened here is, by positioning all these magnets against the repulsive force, we've changed the shape and the orientation of the magnetic field. So a typical magnetic field is a toroidal structure where the flux lines come out of the North Pole, they diverge and go in opposite directions, they flow down the sides, outside edges, and then come back into the South Pole of the magnet. What this magnet array does, with all the north poles facing one direction in the south, is it actually splits the magnetic field in half. As you can see here, this hole, which goes down through the center of the PVC pipe that's in the middle of all of these magnets, also has a rod going down through there that is of a ferrous material. And on top of that, we have a mechanism that's comprised of 3 equally spaced stacks of neodymium disc magnets, the same that are in the actual magnet array that makes up Boris, to show that we can actually interact permanent magnets together in order to derive the energy that is stored within that dimension, within that quantized electromagnetic field. And to prove that, this mechanism will take the energy that's applied to it as we wind it up, and by winding it up, we're basically going to send this magnet array that spins down closer to Boris, which will store that energy in confined flux lines, and then we're going to reverse the process and get the energy back out. It's pretty astounding. So I'm just going to spin this. It may take a couple of times to get it down far enough to be able to store the potential energy. but works pretty smooth. So from my perspective, I'm spinning it in a clockwise direction. And as it spins clockwise, it's working its way down the threaded shaft closer to the face of the Boris magnet array. And you can see as it does so, it slows up. There's obviously more tension up there. So once it's in place, I'm going to leave it right here. We're going to go ahead and reverse the process. You know, a lot of people that deal with magnetics think in limited dimensions. I've studied a lot of permanent magnet motor attempts, and I think the issue that most people find when they're trying to interact with magnetic fields is that they're trying to do it in a limited number of dimensions. Most people think that a tangential force or a rotational force would be the end product of being able to tap into the energy stored within permanent magnets. But they have to move in an additional dimension to be able to make that work. And by that I mean that you have to have the rotation, right, which will take place in a plane that is at a right angle to the vortex of the magnet, if you will, or the vector. The vector. If you know anything about vector analysis, you know we designate magnetic field lines not as north and south poles, but as lines of force, vector lines, which is an arrow, right? There is no north and south poles. It's just which way the arrow is pointing. So now that we've got this wound up, basically, I'm going to send it back the other way, which will basically lift the magnets as they go up the shaft against the force of gravity. These magnets are kind of heavy. The whole assembly is quite heavy, at least it's rotating, so it takes a significant amount of energy to be able to, you know, drive these and continually lift them up. And if I don't stop them, they'll wind to the point where they'll actually come off the shaft. So one thing I do want you to pay attention to is listen for the noise that it makes. It's the most astounding thing. I can't explain where this noise comes from. It sounds like it's from friction. I've done everything I can, WD-40, grease, graphite, everything that I can to eliminate any friction. So the noise is not from friction, if you will. It's not a squealing noise like friction on you know, brakes or a fan belt or something like that. It actually comes from interacting with that dimension, I believe. So here we go. I'll go ahead and stop it there. So we recouped all of the energy that we put into it against the force of gravity. That shaft, if I wouldn't have stopped it, would have continued past the point at which we started, where we applied energy initially to store it. We got it all back out, and you can see it's actually trying to move now. So pretty fascinating.